Hello and welcome to Advanced Particle Physics with me, Will.
And me, Connor.
We're doing electromagnetic radiation and quantum phenomena.
Woohoo!
Yay!
My favourite unit.
Which is really hard. And,
Yeah, especially the photoelectric effect is what you really need to get your head around for this exam, because they do like to ask questions on it, and it probably will come up.
It will come up, Connor.
Yeah, it's going to come up.
The photoelectric effect is one of the key pieces of evidence that light can behave as a stream of particles called photons rather than a wave. If a light were behaving as a wave, then the emissions of the electrons would behave differently. The intensity of the light is proportional to the amount of electrons, but is not proportional to the kinetic energy of the electrons. Therefore, the intensity is proportional to the current in the circuit.
This will make more sense in a minute when we explain the photoelectric effect.
Yeah, okay, we'll come back to that. We'll just say what it is. So, basically, energy is delivered from a photon. First point.
Woo!
Then energy is given to an electron, which is then used to get to the surface and
of a metal which has been cleaned, so there's no impurities on the surface of this metal.
Yeah. And then the remaining energy that it has is used up as kinetic energy, as the kinetic energy of the electron as it comes out of the metal, if you like. So,
just in brief, you get a piece of metal, clean the surface, get rid of all the impurities, and if you shine a light of certain wavelength onto it, a certain frequency, should I say, rather, yeah. It will actually cause electrons to escape from the surface of this metal, and you can detect those with various instruments.
Yeah. And the equation for this is HF, which is the energy of the photon, or Planck's constant multiplied by frequency. We've done this in a previous audio thing, equals the work function plus the maximum kinetic energy. Maximum kinetic energy, we'll come to in a minute. The work function is the minimum energy required for the metal to release one electron. So, if you like, a photon is basically a zap of energy, just like a laser in James Bond. That's a laser that is got energy that is cutting in half. You need a hell of a lot to cut a person in half, but it's the same principle, except it needs less. The work function for every metal varies depending on what metal it is. It depends on how stubborn the metal wants to be
and how big the atoms are in the metal. I know a bit of chemistry here, but
and and so you need a certain amount of energy, and anything that's left is
put into the maximum kinetic energy.
Put into the kinetic energy. For example, if an electron is slightly further down into the metal, it has to use some of the energy to get out. But if the electron was even, I think it's just above the surface of the metal, then the maximum kinetic energy, because it's not using any to get out, the maximum kinetic energy it can have is given in this equation. Basically. And so, yes. Next, as there is a work function, which is a minimum energy required, you have a minimum frequency, because obviously the energy is
proportional to the frequency,
because it's frequency multiplied by Planck's constant. And so you have a threshold frequency. If you see a graph, it will be a line which randomly stops somewhere in the x-axis before it gets to the y-axis. And the gradient of a line is equal to Planck's constant. So if you ever have different threshold frequencies for different metals, the line should always be parallel. Yep. So if you ever asked to draw another line, always it will be parallel, I believe.
If it isn't, you've probably mucked it up.
You've done it wrong.
Yeah.
And then it will be shown by F and then subscript 0, which is the threshold frequency, or the minimum frequency of light for one electron to be released.
That is actually, just a bit of information here, it's actually that's the work function, which is little symbol Greek phi, or I can't remember what it's called. It's a little O with a line through it. It's that divided by Planck's constant, just in case.
I know what that is. Harry Potter, Deathly Hallows.
But there's no triangle.
There needs to be a triangle, but that is basically the symbol for the
Deathly Hallows. The wand, the
wand,
stone,
and the
invisibility stone.
The wand and the stone.
Oh, the stone for dead people.
The cloak.
And the cloak.
I don't know, where is the cloak?
I don't know.
I never got it. Was Harry's invisible cloak? Was that the cloak?
I think it was, but
was that the cloak?
Yeah, it was the Elder cloak, whatever it's called.
Was it really? I don't think they hinted that enough.
They didn't do it. Well, she kind of made up as she went along, didn't she? She's just sort of saying, right, how can I make this?
No, she wrote. Well, yeah, but still.
I don't think she wrote the first book thinking, right, he's a Horcrux. We're gonna. Oh, sorry, if anyone hasn't read the book yet, I'm so sorry. I'm so sorry.
Nothing. Stop talking about that. Right. So the line, obviously, if you do maths, if you just generally have a brain, you will know what y equals mx plus c means, and that is proportional to the equation if you just move it around a bit, which is ek, or the maximum kinetic energy, which is subbed in for y, equals mx, or hf, plus c, because xf, minimum threshold frequency, or
Bingo.
the different frequencies as x is a variable, m, which is a constant, which is h, which is 6.63 times 10 to the minus 34, plus c, which is the work function. For example, if you were to carry the line on past into a negative y value, then you would eventually, it would hit the y-axis, and that is the work function, I believe.
I think that's the kinetic. Oh, no, you're right. Yeah.
It is the work function. You're wrong.
I'm wrong.
You're wrong.
I admit
So it wouldn't be a negative, obviously, it would be a positive. It's just the way it sort of looks. So
it's stupid.
yeah, okay, right.
Moving on.
Moving swiftly on. And so, if we go back to the first thing that we were saying, if you, you're shining a light on, imagine you put it in a circuit. So you've got a metal on one side connected up to a circuit, and then you've got a charged plate, is it? A charged plate, and then a gap in the middle. If you shine a light on the metal, it will release electrons. They will be attracted to the charged plate, and a current will flow, because the current is a flow of electrons in the circuit. What it's saying is that if you shine a light on the metal surface, if you increase the intensity of the light, you would expect more the electrons to have more kinetic energy, because they've got more sort of
it's just
light,
common sense, really.
Yeah, exactly. You've got more energy coming onto them. You expect to give them more energy. However, it doesn't do that. It just has more electrons with pretty much the same kinetic energy, or the same as they would have had if you had
different intensity.
Whereas what's the other thing that you can do to it? If you have intensity, the frequency. That's right. If you increase the frequency of the wave, then you would expect the other thing to happen. You'd expect them to be more of them, because you've got more frequency with relatively the same kinetic energy, but they have more kinetic energy, which is evidence for the wave,
the particle nature.
Wave particles. So, if it was to conclude, if it was a wave, you would expect a time delay for the energy to build up as well. That's another point we didn't touch on. If it were a low frequency, if it were a low frequency, so if it were below the work function, after a while you'd expect a build up of energy and then at least one electron release, but this doesn't happen. So this is saying it's a wave, and a high intensity should give more kinetic energy to the electrons, but it doesn't. Particle evidence is that one electron absorbs one photon.
So something you've got to take into account. You're sort of assuming it's true that one electron does absorb one photon. There's no
which is why there's a work function, because it has to get enough of that one electron to get out for one photon. And the emission is instantaneous. There is no time gap, and electrons are only released above the work function.
Yeah.
So that is all evidence for a
particle nature of light, the existence of photons.
Yes. So, and moving on to excitation of gas atoms. Electrons in gas atoms can absorb discrete quantities of energy, making them excited.
No, not...
Like they're having a party.
No.
They're having a party.
Effectively, this is all quantum, they jump from one energy level to another, and if it becomes excited, it has more energy than it would normally.
Except they don't jump, do they? They sort of disappear at one place and appear at the next.
Jumping is an easier thing.
They don't jump though.
They don't really, admittedly.
They're not like little excited kangaroos.
But the point is about these
little
electrons.
Party kangaroos.
Is that these electrons do become excited. They do jump into a higher energy level.
Well, they don't jump.
They become a higher energy state.
Yeah, I'll accept that.
And then instantaneously, they sort of lose that energy. They jump, or they appear and reappear, whatever, back down into the energy level originally that they were at. And this actually causes the release of electromagnetic radiation, or waves,
or a light, basically.
It's
the easiest way to put it.
Thing.
The absorption of a quantum energy has put the electron in a higher energy state, and the energy is then emitted as a photon of electromagnetic radiation as the atom returns to its ground state, which is the minimum amount of energy that an atom can have. This usually happens in 1 nanosecond.
So it's almost instantaneous.
Almost, pretty much is, right. So, basically think about it. You have your atom and a whole load of orbital electrons, and an electron comes flying in from somewhere.
somewhere else. Say
But yes, from say
you're firing electrons at it because people.
Australia.
Australia. Yes.
Very miffed at us, Australia.
Oh God, they're making an electron
We have stopped
gun.
watching Neighbours and they've stolen Downton Abbey.
How dare they?
So, they chuck an electron over at us, at our giant atom in the sky. Don't write this in your exam.
Do not write this. This is
The electron then hits what?
The atom.
The atom.
Yeah, at some stage.
Hits the atom.
Yeah.
I'm not going to lie, okay? We recorded this,
A good
then
few
realised we
times.
had no idea, stopped and spent the last 10 minutes researching this.
And we've discovered that the highly detailed textbook says that the atom absorbs energy, so we're not sure what it hits. Or
It doesn't
what
matter.
hits it.
Stop. Okay, we know what it hits. It basically hits the atom.
Yes.
It absorbs the energy, and the reaction it has is it moves electrons from certain levels to a higher state, so a higher level, if you like, which means they're excited. So that could be from the ground state to a higher state, or it could be
from stage
even
1
higher.
to 2, or it could be anything really.
But the easiest way to think of it is from the ground state to a higher level.
Yeah.
Which is by absorbing the energy, but that is unstable because you've got if you've got electrons that are naturally sort of they need to be in a certain order, as you might have done in chemistry. They're now in a further out, which is just annoying. So they de-excite, and the process of de-exciting releases a photon,
electromagnetic radiation,
or electromagnetic,
or light,
light of frequency proportional to the energy. Again, proportional to HF is the energy. Planck's constant and everything, and then that de-excites. It can de-excite in several levels. Say it's on level 3, it could de-excite to level 2, then
or to level 1,
then to level 1, or all the way to level 1. And however it de-excites, it will emit photons of whatever the energy is. So it could emit 3 photons, or it could emit 1 photon that's got more energy. But the energy is the same.
Energy.
So if they asked you to draw all the possible sort of outcomes and everything, you could draw, basically, you look at the levels they're asking you, and you just find out how many different combinations of arrows you can draw. Yeah. Only in one direction going down.
Yeah.
Electrons in gas atom can absorb discrete quantities of atom making them excited. We've done that already. Graphs show the excitation potentials, is what those awesome graphs look with n equals 3 and stuff. For a particular atom, it can be through you can think of it as a cross section of an atom. Yeah. So think of the little orbital electron. That's basically what it's showing. An electron is excited when at a higher level than the ground state, and an excited atom has extra quantum energy, leading to electrons jumping in inverted commas. Shells emitting excess, and then the de-excited emitting excess energy. And that's how you can think of it, basically. Yeah, anything else in that?
I will just point out that the electrons can only absorb so much energy. They're discrete packets, so you can't change the level of energy to whatever you feel like. You can only excite.
Yeah, the levels are,
set.
Yeah, exactly. So one question that I saw, it was something like, these 2 electrons of different levels, and they had their energy signatures. And it said that photons, one photon was fired at them, and one of them changed its energy or changed its level, if you like. The other one didn't explain why. You should say that there are discrete levels, there are discrete energies that the electron can have, and it can't. There is no gap. There's no sort of
in between.
It's line Spectra, which we're doing in a minute. First, quickly, ionization is basically it's got to the top level or the infinite level. It's got out of the levels, if you like. It's gone to the top floor, gone to the roof and jumped off of the building. Flown away is better.
Yes, it's been.
And ionization, and that's if you give it a threshold energy, if you like, then it will be ionized. Anything above it would just be kinetic energy.
Yep.
Out of that. Fluorescence is quite simpler than it sounds, I promise you. An atom in an excited state can de-excite directly. We've just done that, producing photons of equal energy. If any photons are in the visible range of the electromagnetic spectrum, then it will give out a light of a characteristic colour. The fluorescent tube that you might have on your ceiling right now is made more efficient by having a coating which can absorb UV photons. And then the coating atoms de-excite electrons emitting visible light. So imagine it as you have your atoms of the metal within your fluorescent tube. It emits a whole load of fluorescence by de-exciting.
different levels of energy.
But
So
then-
you've got UV, infrared, and all that.
Yeah, if you have UV, then you
Kind
know
of wasted energy.
you
You can't
don't
really see
you
it.
can't see it, and it's a light that's ruining it. So the coating, think of it as another metal or another atom. It de-excites again, and
Sort of converts the
emits visible
UV
light.
energy.
So
Into...
literally, it's like double doing it. So
Yeah.
it's emitted UV, and then you use the UV as the incoming
source.
photon to excite and then de-excite as visible. That's it. It's really that hard. So you can think of it as a second de-excitation graph, if you like. I have an example question here, which is describe the process by which mercury atoms become excited in a fluorescent tube. This is the ideal answer. Electrons flow through the tube, and an electron of a certain threshold energy collides with an atom, causing the energy to be transferred to the atom. This causes electrons in the higher shelves to jump shells, releasing the excess energy as a photon or a series of photons, depending on the de-excitation. Anything wrong with that?
No, nothing I can see.
There we are. That's lovely. Right. Energy level questions. If they're asking you, these are just little tips. If they're asking you for the smallest wavelength, it means the biggest energy level, meaning it's going to have a bigger frequency. But the smallest wavelength, I believe, will have a higher frequency, the biggest frequency. So if they're asking you for the air de-excitation or excitation with the biggest wavelength, you pick the smallest gap between the levels.
Frequency. Frequency is indirectly proportional to wavelength.
Yeah.
Well, actually,
So
frequency is 1 over wavelength.
Yeah.
So yeah.
It's the reciprocal, yeah. So to calculate the frequency of an emitted photon between energy levels, use the difference in energy. So it's HF equals E1 minus E2.
Yes, I believe so.
Even though they're minus energies,
You take them as positive.
you
really.
take them. Well, no, you take them as negative, and then the minus in the middle will cancel it out. And what it's doing is it's finding the difference. So if you have minus 4.9 electron volts and minus 13 electron volts, minus 4.9 minus 30 minus 13 makes it plus 13, which is basically 13 take away, which is the difference.
Yeah.
Take away 4. That's basically what it's doing. Now, line spectra. The wavelengths of the lines in a line spectrum of an element are characteristic of the atoms of that element. By measuring the wavelengths of the line spectrum, we can therefore identify the element that produced the light. This is because energy levels are unique to an atom. Each line in a line spectrum has a certain colour due to the certain wavelength, and the photons that produce each line have the same energy, different photons producing any line. Basically, think of energy levels, but it's backwards. So you can see the light that is being produced by the de-excitation, but you don't know what metal it is. And because, as we said earlier, electrons have a characteristic energy states, you can see they have characteristic photons, and you can see them as in lines.
Yeah.
As literally lines. And you can see by the colours of those lines the wavelength of those lines.
The wavelength
and then you can tell the frequency, and then tell the energy, and you can tell what
the element.
The element
eventually.
Which is all lovely. Each photon is emitted when an atom de-excites, etc. We just said that. And yeah, it is E1 minus E2. And emission lights, if you need the lingo, if you like, the lingo.
Killed yourself.
Emission lines are the bright lines, and absorption lines are the dark lines. And it looks awesome. Very quickly, just very something simple. It's really easy. You don't really need to know.
No, it's not.
Really, just going to touch on it is a wave-particle duality,
which is a extremely hard subject matter.
De Broglie, or the person I like to call Mr. Broccoli.
Debris.
Mr. Broccoli.
He's French, so his name is spelt
Don't
Broccoli.
get word, Mr. Broccoli.
He was a radio
Suggested
operator.
that particles could behave like waves. He said that any particle could be thought of as a wave with a wavelength. So the wavelength equals h over mv. That's mass times velocity, which mv is momentum, which is also known as p. So if you want to find out your wavelength, then you times your mass by your velocity, and then do Planck's constant divided by whatever that is, which is your momentum.
And you have your wavelength.
Then you have your wavelength. And that's all you need to know. Velocity, you can also think of it as speed. So if they ask you for the speed of it, then you'd give the velocity. The mass, they'd usually give something like an electron or a proton. That is either 1.67 times 10 to the minus 27 or 9.11 times 10 to the minus 20 something.
It will be on your formula sheet.
It's on your formula sheet.
Yeah.
In fact, I have it right here. It's 9.11 times 10 to the minus 31. I was close. I was only one digit out.
Only
I said 30.
1 to the power 10. Between 10 and 100, basically.
No, I was one out. I said 30 and it's minus 31.
Yeah.
I said minus 30, didn't I? Anyway,
Yeah,
stop
you
it.
did.
So yeah, you just work that out, mass, momentum, etc., etc. That's measured in meters because you have joule seconds over Newton seconds. That's another thing. Momentum, you need to know that's measured in Newton seconds. Or yeah, basically, because it's kilograms multiplied by speed, which is meters per second. So that's effectively kilogram
Per
meters per second.
Yeah, kilogram
Not
meters
per,
second.
just kilogram meter per second. Or you could also get them up for putting kg ms minus 1. But that's just really confusing. So just don't even do that. Just put Newton seconds.
Yeah.
And yeah, electron diffraction is basically evidence for wave particle duality. It's the very last thing I do promise. A narrow beam of electrons in a vacuum tube is directed at a thin metal foil. You can do this one. I've been talking too much.
Right. The beam of electrons are produced by attracting electrons from a heated filament wire to a positively charged plate which has a really small hole in its centre. So we're drawing electrons off this wire, this charged wire with current flowing through it. We're drawing it from with these positively charged plates with a hole in the middle. So these concentrated streams of electrons. And what's really interesting about this experiment is if you put, say, one slit in this, say easier, 2. If you put 2 slits in this experiment, and you put equipment to identify whether if it's a wave, if light is a wave, or this electromagnetic, blah, 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 electrons are a wave, you come up with a distortion pattern, this interference pattern, which is characteristic of waves. However, if you then turn off the wave detecting equipment and then put particle detecting equipment, you come up with a much more characteristically particle based example. So but the thing is, it sort of changes depending on what equipment you use.
You're not making any sense.
I'm making perfect sense.
I know what you mean. Basically, what Connor is trying to say is that the electron knows whether you're looking at it or not. If you're looking at it with particle equipment to see whether the electron is going in the first slit or the second slit, it will go, one electron will go in one slit, another electron will go in the second slit. But if you stop looking at the slits, then it appears to go through both because it diffracts like light does through both of them, one electron. So it sort of knows whether you're looking at it, which is
really
basically
odd.
Yeah.
Wave particle duality.
So that's it. Yeah, to a charged plate, and you can see rings basically on the thing at the end of the tube, and they form a pattern of rings on the fluorescent screen. That's what I just said. That was in English. Thank you if you have listened to now.
You are very, very brave.
You are one of the minority, because I don't think even I will listen to now if I listen to this back.
At all.
Thank you very much for putting in the time.
Sticking with us.
You will now get an A. If you listen to the next, what I expect will be about 3 audio things on electricity. Thank you for listening with me, Will, and Connor Durkin. We're gonna go and have some lunch. Yay!
Lunch.